Morning, everyone. I am Kal, and this is Aziz, and we have another member, Vishal, and we'll be presenting our work done on the Spear library. So first, so Spear stands for Semi-Supervised Data Programming in Python. So this library is part of the Decile libraries, and the main goal was to make accurate models using limited label data, and doing it all in Python. That is the main aim of this library. Yeah, so this is the basic pipeline of what Spear actually does. We have ways to design our LF, and it basically gives us uh, functions from which we can easily make our own labeling functions however we want. And these labeling functions can act on labeled sets as well as unlabeled sets. On labeled sets, like on unlabeled sets, it gives us the coverage that how much of the unlabeled set is actually covered by the LF. And all these we can use any of like six. There were six label aggregators which were there in the paper, I think, and like you can make more also if needed, but these were the main six mentioned. This is the basic Spear pipeline. So now our aim was basically Spear gives us ways to make labeling functions. It gives us all the techniques, but it doesn't actually make any labeling functions. Like we only have to define it. So we wanted to integrate few automatic labeling functions to make the process easier. So what automatic labeling functions do is they convert text into a smaller subset, like a representation, like tokenization, which can be easily understood by the computer. And this is often a logic expression or a semantic representation. So an example for this could be like if we have our IMDb data. And in IMDb data, we have a plot of a movie and the genre of a movie. So now the plot of the movie, and we have a limited set of like this plot gives the genre as romance, and another plot gives the genre as action. So what we can do in this, if we have very less data, we can figure out few keywords that if let's say if my plot of the movie has the word love in it, then definitely it's going to be a romance movie. So if you can find a shorter representation of the plot, then we can easily predict what our output is. So this is why automatic labeling functions are pretty useful. And we have done, so these are methods of automatic labeling functions. And we basically automatically get rules from the data. It uses more or less heuristic methods. So one of the methods is we use decision tree approaches or the weights of a classifier, and we find some pattern in the data. It's like kind of semi-supervised. And using this pattern, we get a few noisy labels. And after sending this to the aggregation, we can get noisy labels for the whole data set. So that is the whole idea behind automatic labeling functions. So one of the methods we used was Snuba. So this has already been done in another paper. So there was a paper based on this, and the point of Snuba was first it generates the rules using a label set. So it takes in a label set and finds a few rules, and then filters heuristics based on precision on the label set and coverage on the unlabeled set. So from the label set, it takes a fixed set of rules, and heuristically it finds patterns, and tries to on an unlabeled set make find maximum coverage as much as possible. Like in the IMDb thing, I want to try to find such a word such that it is present in most of the movies of that genre. So that is the whole point of this, and it finds uncovered points or abstained points in the label set. So this is the third step. So basically, it repeats the first two steps for a long period of time till it gets enough coverage, and then after it finally gets enough coverage, it is put on the label set, and it gets the uncovered points, which were not which we couldn't find enough data for. And another model for this, which we used was the the classifier weights model. So in this, linear model classifier can be used. And this is basically more or less like logistic regression, where we have a few n instances and we have a feature matrix, and we are just training a basic classifier model and getting the weights. And we use a sigmoid function because, activation function. And we get a few largest weights in W, and using these weights, we get our labels. And we tried, so in this one, like logistic regression was already implemented. We tried implementing a few different types of models also, like logistic regression with different kind of penalties. And we tried using an SVM model also. But more or less, these were giving like pretty much similar results. So there was not much improvement, but it was just an experiment we could think. Yeah, so now Aziz will be explaining, he'll be showing the code for what all we've actually contributed. He'll show it. And Aziz, you can share your screen,
Yes,
right?
yeah, just share my screen.
The third student is not presenting at all, not even present here.
Yeah, he's stuck somewhere. He just joined. Uh, he's on as well.
Yes, so he's with me right now. I'll just switch on my cam. Basically, he had a presentation which just got over. That's why up another
Oh,
goes.
okay. Yeah, it'll be good to have your cameras turned on whenever possible.
Can you see my screen, sir?
Not yet.
Oh, can you? I think
Yeah, it's
you should be able to
visible.
see my. Yeah, nice. Yeah. So, sir, as Kalb said, Spear initially didn't. I mean, it didn't have any of the auto generation libraries integrated with it before. So what we have done is, um, we have these two approaches. One is Snowba and one is classifier weights, and we try to integrate them into the Spear pipeline itself, so that it can be called whenever the Spear package is called and used appropriately. So for that, we already had the code in separate files. We just created a class, uh, getting all the code together so that it can be called, and with all the functionality in the argument so that it can be called appropriately. And this has all been tried and tested, and the labeling functions are being generated and stored as it is required. So for that, just to show this, we have a couple of notebooks that we can run that we have run just to depict the functionality, and this can be there in the repo itself as examples, like that it was there for the labeling part as well. So you can see that there are two classes, LF generator and LF generator 2 for Snuba and classifier ways respectively. Um, and this is how you can import the class from the data set, and DT is just the model that we're going to use for Snowball. And all these
So
arguments can be passed there.
have you implemented Snoba exactly? Is it that you've
No,
implemented
actually,
or the first
Snowball,
two steps
sorry.
or have you implemented the first two steps of Snoba?
No, the all three steps. I mean, the pipeline is implemented. The Snowball pipeline has been implemented. Um, it was already the code was already there, but it was just not in one place. We just uh, sort of got everything together.
Okay, Ayush, was this not done already for Wisdom or for Precise?
No, sir, this was not integrated into the library itself. The code was present because we did it for the ACL 22 paper, but it was like splintered. For example, FAIR has classifier weights, but the 22 paper didn't have. So I gave them the code and the directions to do it, and they integrated them into the library.
So it's completely integrated, Ayush?
Sir, they sent me yesterday. I didn't get a chance to check completely. I have asked them to put the documentation as well on read the docs for the things that they have done. So I have to confirm that, check it. I haven't checked it yet.
Please go ahead, but I also want to test you people on how much you've understood the bi-level optimization problem in the wisdom paper. Since this is a CS769 project, right? I would want to make sure you understood the optimization problem you're solving. But you can do that a little later. Yeah.
Okay. So I'll just go through this one IPy and then. So as you can see, we're calling the other generator function, and this is just the representation of it. Then we can load the data directories and save directories, and call the functions so that it generates the labels, and you can get the accuracy and coverage information as well. Um, this is what the function returns. It gives you the labels corresponding and the labeling word that it has identified. For example, over here, 0 corresponds to romance movies and 1 corresponds to action movies. You can see some correspondence between them. And then there's this dump function where it just takes all the information and stores it as pickle files in the save directory that we defined. And a similar functionality we have implemented for the classifier weights as well, which is LF generator too. So this does pretty much the same thing, but just the algorithm is different. And we have tried this on several data sets. We have documented this for IMDb and SMS data sets that were already there in the repo. Yeah, so this is what we've done.
So, Aziz or Kalp, anyone can answer. So, in your experience or in your using this while using the all these approaches like classifier weights, SNUBA, and others, what do you feel is lacking in these LF generation approaches? Observing over the LF they have generated or the altogether the methodology, anything, it's fine.
Um, yeah, so what we were trying to do is we saw that the coverage wasn't very good in these approaches. Like, for example, in the classifier weights, it's very easy to understand what is going on, but the coverage wasn't as good. So what we were trying to do was trying out different models that use weights in their own structure, and trying to sort of implement a similar thing as logistic regression, but with those weights, to see if we can get any improvement on the coverage. Because if we do, then we can sort of have some sort of explainability there. And we did that, and but we didn't get any. You can see the spreadsheet, I suppose.
Mhm.
So we did try it on two different forms of logistic regression and SVR. But as you can see, the three colors indicate the individual coverage of individual labeling functions for the three different methods. So as you can see that they are more or less similar. I mean, we have one word that covers a lot of the data, and the others lying in the 0.2 range
Mhm.
is 20% coverage. So we couldn't find any improvement over there. But I still think that there's something we can do over there, because the coverage seems really low as compared to, um, let's say, because the accuracy is around 80-90, but the coverage is only 40%, which is sort of uh, not workable, right? Because if you're abstaining from most of the labeling, and so we're trying to get some improvement over there.
Right.
Yeah, and also in general, using labeling functions and semi-supervised methods, like they don't give as good accuracy as supervised methods, I think. That was
Exactly,
one
right.
of
That's expected. But what do you feel from your optimization course can be used to, as you mentioned, to increase the coverage of the whole set? The complete set is there, which has like, let's say 100 labeling functions, and then you are selecting few out of them. So what do you feel from your optimization course, the learning from that course that can be utilized to select a set with a higher coverage?
So this is what I was thinking initially. I'm not really sure, but what right now we are doing is we are iterating again and again over a small subset of label set, and trying to find good labeling functions for that. But we can sort of try and implement a sequential sort of pipeline where we get a label set, get some labeling functions for that, and then try that on the unlabeled set, and then from the subset of the unlabeled set which is not covered by this, somehow we can get a correlation between them and a subset that we choose from the label set, and then try and get labeling functions on that label set, sort of like what you do in boosting in decision trees. But the main I think uh, main problem over here is how do you relate the uncovered data from the unlabeled set to a subset in the label set appropriately, so that you can get the coverage that you require. But that can be one idea that we can use sort of to extend the coverage issue over here. Uh,
Yeah, but yeah, right. We can, yeah, think about that. Okay, go ahead.
uh, so yeah, that was something that I've thought, but I haven't implemented
Why
that
would
any.
use of the label set help you improve coverage? So have you not been
Uh,
attending my recent classes where I explicitly talk of coverage as a
no, sir.
discrete
The
function? So we can use unlabeled set, like coverage on unlabeled set as a criterion, right? And coverage functions are submodular functions. You could try and optimize for them.
No, what I meant is, sir, because if you're making a new label function, you will need the labels so that you can assign, so that you can understand like which word is correlated with the corresponding labels, right? And then we're trying those. Uh, uh, we're trying. Let's say, for example, I see that there are 50 cases of romance movies, and 49 of them have the word love in them. So then we can say that okay, I identify love as a priori to say that a movie is of genre romance, and then we try that love word on the unlabeled set which we don't know the genres of, and see how many actually we can how many of the unlabeled set we can actually give a label to. So for example, if the unlabeled set have 200 movies, and we have 25 of them which have the word love in them, so we could assign a good we could assign a confident label to 25 of them, and so the coverage is only 25%. This is sort of just one labeling function. Now we can have a series of labeling functions and aggregate them so that your coverage is more on the unlabeled. What I meant. Uh, I hope that makes sense. Uh,
I did not understand. Can you repeat?
so sure. So what I meant is the reason I need the label set is because I want to understand how the words in the data of a movie corresponds to its genre. For instance. So once I identify that, then I can try the recognized words on the unlabeled set of which the genre is not known. Um,
Can you please go slow?
so
I can't understand anything you're saying. Can you go slow?
sure. So uh, am I audible? I think it's because my phone is kept
Yeah,
away.
yeah.
Yeah. So what I'm saying is, let's say in the labeled set we have a genre called romance, and we find that maximum movies that have the genre romance have the word love in them. So we identify that love is a good priority for us to say that a movie belongs to genre romance. Um, and then we try that word love for the on the unlabeled data set of which the genre is not known a priori. And we see how many of the movies actually contain the word love in them. So that gives you the coverage on the unlabeled data set. That is why we need the labeled data set also to sort of try and better the coverage on the unlabeled data set.
Yeah, yeah, that point is well taken. We need to bootstrap always around the label data set. Right? Even if it's small, we need to bootstrap around the label data set so that the words, features, whatever we are trying to cover, they resonate well with the target task. But then also in the process, um, improve the coverage on the unlabeled. But see, this is easier said than done. This has to be posed as a very nice optimization problem because the notion of coverage can be transitive. So let's say there are words W1, W2, okay, in the label set. And if W1 and W2 co-occur frequently with a word W3 in the unlabeled set, right? Or let's let's say I'm trying to identify those words in the unlabeled set which frequently co-occur with W1 and W2. which are strongly associated with the target label. Now that is also helpful. I mean, these words W1, W2 itself may not be frequent enough. They may not have a good coverage, right? So we'll have to bring some kind of a transitive notion of coverage. The notion of coverage cannot be straight jacket. It has to be somewhat transitive. Do you understand? Hello, am I audible?
Yes, sir, I'm following you.
Yes.
So yeah, so we can, but if W1 and W2 are sort of correlated with W3, then shouldn't that mean that the coverage of W1, W2, and W3 should be sort of similar because they are occurring together? Or are you saying correlation in the sense of the label only set?
Yeah, so W1, W2 may occur. So wherever W1, W2 occurs, W3 occurs in the unlabeled set. But W1, W2 may not have high coverage. It's just that they are strongly correlated with W3, and W3 may have high coverage. Understand now?
Yeah, yeah, I get your point. Uh, right, so that maybe can be a sort of way to extend the coverage in this scenario.
Yeah. So can you think of some interesting optimization problems? Um, this is really an optimization problem, right? Give me a bunch of features or feature representations which have high correlation with some representation on the label set, but have high coverage on the unlabeled set. Okay. Isn't that an interesting problem? Feature representation. I'm typing it. I don't know if you can hear me. Feature representation
Yes,
that
uh,
is highly correlated with representation in the label set, but also has high coverage in the unlabeled set. So this is.
so
Can you try and pose an optimization problem on this?
So, so a way to maybe formalize this maybe can be um, to iterate over all the words when we're dealing with the label set to maximize over. So to identify some labeling function and to maximize your correlation over um, of a particular labeling function over all the other labeling functions, and then to maximize the coverage of that over the unlabeled set. Uh, so maybe if you
Can you
have
repeat? Can you repeat once more?
right. So what I'm saying is a way to formalize this can be to identify first, start off with identifying some labeling functions from the label set, and then trying to maximizing the correlation between them. Right now, just only looking at the label set only. And then from that maximization problem, trying to maximize the coverage of those functions of those words over the unlabeled set. So that can sort of you can sort words in that order and try to get those which are highly correlated as well as have high coverage in the unlabeled set. Uh, uh, am I mean, was I followable?
Yeah, you're saying the same thing which I said, right? I don't see any difference.
Yeah, that can be
I've
no.
typed it.
I'm
I
saying
typed it on the chat. Is that what you're saying?
just 1 minute. I'll check.
We have no access to the chat.
Oh, we can't chase with the chat.
So just a quick question, everyone. Do you think that submodular subset selection kind of approach would be useful for selecting a higher coverage set or a more useful subset?
Uh, I mean, with the aim with subset selection was that we don't want to work with a lot of label set for our computations. We just want a small representation of the entire data set, right? Uh, so if we even if we get a very good representation.
Don't have to say small. I mean, it is some budgeted. See, small is doesn't mean that it's compromised. It's budgeted because too much redundancy doesn't help. But this can have high coverage. Looks like you've not attended my lectures over the last 1 week, right? So I've been repeating this again and again. The subset can have very good representation overall, or have good coverage on the features. It may be small. It may be small in the sense it may have a budget constraint.
Right. Yeah. So I mean, what I meant was that even if we have I mean, a subset of the entire set which has a very good representation, I mean, it's hard to say if we can get a better coverage than, for example, using the entire label set, because uh, we sort of our aim was to get a good representation of the entire set in the first place. So we're not doing anything. We're not getting anything extra from. Uh, I mean, we're only getting the advantage of using a subset is only computational, as far as I understand it. Uh, if I mean, so I don't. I mean,
It is
I
not.
don't see
It is
how.
not. No, no. It is not just computational. Please understand. It is not just computational. It is. It can be related to cognitive load, obviously, because you want to make it compact. It can be possible to have. If it's compact, then you'll avoid overfitting. So don't just reduce it to computational. You're trivializing it too much.
No, no, that's not what I meant. I meant that uh, we have some information, and based on that, we are trying to do the best we can for the coverage on the unlabeled set. But we are not doing anything extra by doing subset selection. We just um, uh, I'm not able to explain very nicely.
No, no, no,
So
no. So again, please go through my lectures of the last 1 or 2 this week at least. Uh, I mean, you can have let's say you have a big DAG. Okay, you have a DAG in which these points of the search space of all possible nodes are organized. A directed acyclic graph. Okay,
uh, okay,
so you want to identify a subset from the selected search. The search space itself can be large. The search space is of hierarchy is hierarchical in nature. So the problem of induction is basically of that nature, where you are trying to identify a subset from a very large search space.
okay.
Right? So you
Uh,
understand that a DAG, right? Directed acyclic graph. You have a node, um, and its parent could be the generalization. So if you have conjunctions of two words, a conjunction of two words, its generalization is just each of those words. It can be two generalizations of conjunctions of two words. So as you go down in the DAG, you're conjoining words. As you're going up in the DAG, you are coming up with simpler words, right? Not combinations.
mm, yeah, right. Yeah, I get your point. Uh,
Okay, so can you answer questions on the bi-level optimization, the paper you have implemented? Can you present, go over the paper? I mean, I want to make sure you understood the paper itself.
The paper regarding wisdom, that one.
Yes, yes.
Okay.
Yeah, the paper is over here.
No, not this, not this. There is one more paper, which I gave you the archive link, na?
Yeah, yeah. Just learning to robustly aggregate
Yes,
labeling
yes,
functions
yes.
for that one, right?
Right, right.
Okay, Kal, you can present. I'll stop the
Also,
recording.
they implemented both, is it? Fair as well as wisdom, right?
Uh, Sir, one part of the fair, like using classifier to induce rules by looking at the top weights that is produced by the classifier and associating them with the features. So they have implemented that part. Yes, they have. So, but I have not gone through their implementation because I have to check that again. I'll come back on that.
Okay.
Is my screen visible?
It's just, yeah, it's just,
Go to that implementation methodology part. Yeah, this one, equation 6. Equation 6 and 7, yeah.
With the combination of losses.
And 7, show the 7 equations.
Yeah, can you present your understanding, please? Are you explaining anything at all? Can't hear.
Yeah, do you want me to, I mean, do you want us to like explain how the
Yeah,
loss
yeah,
terms came out?
yeah, yeah. What are the loss terms? I mean, it's your optimization viva, right? I want to know how much you understood the optimization problem here. So please present your
Oh,
understanding.
fine. Yeah, I think they combined 7 different losses, and they have actually explained what all the losses do. Like most of they have three cross entropy terms here, and you have a KL divergence term, and here I think up over here, yeah, here they've explained okay,
No,
how they've
be a
gotten the
bit more
terms.
precise. Be a bit more precise. Anyone can see that scale divergence. Scale divergence between what? What are the parameters? Why is the bi-level optimization required? What is W versus theta versus phi? Get into some details, please. This is hand wavy. You need to get details.
Okay, sir.
Have you not read and understood?
Yeah, we read and like understood why they were required, but we were mostly looking at it from an implementation point of view, not from a theoretical
Yeah, but
point of view.
if you said you have read and understood why they were required, then okay, why and what? Explain the why and the what, right? Explain the theta, phi, W. You said why you understood. So why is there a 6? Why is 6 required? Optimization problem in 6. What is why is W required?
So actually, this is not what our focus for this deliverable was. We sort of only focused on the working of the
No, but
generation part of the labeling.
this is the paper you implemented, right? I'm asking you for a paper that you implemented. What is the optimization problem? This is a course on convex optimization, right? Or on optimization and machine learning. What are these optimization problems? What is Seven doing? None of your none of you can answer anything at all.
So this is sort of how they're uh, coming up with. I mean,
Someone speaking, I can't hear anyone. Is someone speaking? Actually, I can't hear anyone. No.
yeah. Um, Actually, we won't be able to explain it in a detailed way, sir, because it's not what we have.
But not detail in the sense you're not even you're just saying you're just reading KL divergence. KL divergence between what? I'm not asking for details. KL divergence between what? Do you want a chance again afterwards? Because I mean, you're not understood what you implemented, right? Why is this? I mean, when you say something doesn't work, something works, how will you know what works, what doesn't work if you don't know what you implemented at all? Hello, there's some
Yes.
radio sound.
Yeah. Right. So,
Isn't
um,
this the goal of the course, right? Understand optimization problems and then implement algorithms. You have implemented, not you haven't really implemented, right? They have not implemented, they have just integrated an implementation, correct?
Yes, sir. So they have integrated the first part of generating the labeling functions, not this bi-level framework.
And that part is not yet, they have not touched it at all, is it? Or they are yet to
Yeah,
do it.
yes, yes. Yeah. So step one was to develop this automatic generation of the framework of LF framework. Then go on to that optimization part. But I was not sure of the scope, so
No, but
I,
this is a three-member team, and this is a very high weightage NSEM project, right?
mhm.
Isn't this too less? I mean, um, at the least, I would have expected them to understand the optimization problem. That's like a given. They would have okay. I think a bare minimum would be that they implement the feature enumeration part and they understand the paper. They haven't understood what's happening here. They have, and you're saying they have kind of implemented the first part, right? Just integrated the first part, or is it
Yeah,
implemented?
we've like used only we've only done with the smoother part. We've not gone through the whole.
You have integrated or implemented. Again, 2.2. Have you integrated or implemented? Ayush, 2.2
Integrated, right? Yeah, integrated,
Yeah,
right?
we've integrated. 2.2 we have integrated.
Yeah, so I mean, this is too less work, right? For a project of 3 people, I think this is less work. I'm saying at the least you should have understood. You've integrated 2.2, not even implemented, and you could have understood at least the remaining part of the paper. But you've not even taken that effort.
Well, okay, can we so I understood what our shortcomings are. Can we sort of get another chance at this in some time maybe uh, where we can understand everything that we require to and come back.
Yeah. So I think bare minimum is understanding paper and what you have done in this integration. Ideally, you should have also integrated. Ayush, ideally, you should also integrate the second part.
Yes, sir. That was the plan. Integrate both the parts. I was not
So,
sure of
oh,
the.
they were to integrate both parts, is it?
Yeah, yeah, yeah. I mean, initially I told them to get the implement part one, and then I was not sure of the scope of the how much percentage of the whole marks does this project consist of.
Oh, it's a significant weightage, 20%. Yeah.
Okay,
So they all know, students know.
okay, okay. So yeah, if that is the case, then yeah, that is because the code is already there. They just have to clean up and integrate into the library
Yeah.
properly.
So what is the big problem, right? Please do that, right?
Yeah, we'll do that. Uh, and we'll sort of get a good enough understanding of all the papers that are related to this also.
Yeah. Okay. Let's writing it on the chat here. Copy paste it. Anything else?
Nothing else from our side.
Shall we exit?
Okay. Okay then. Thank you. Thanks. When will you present? By the way, when will you present?
Uh,
When will you?
what time? I mean, say in 1.5 weeks time, if we can get a slot to present again.
Yeah, put it in the sheet. Okay. Okay.
All right.
We'll have to put it in the sheet.